Okay. I think we can start. Yeah. Okay.
Do we have a pointer or something, Ruud?
No,
A clicker?
I don't have a pointer here. It's not here, so we have to use the keypad, I think. Welcome, everyone. Rather a small audience. Well, but that's a good thing, I think, because then maybe we can also have some discussion and get some input from you. That will be nice. So,
Would be nice.
because we're talking this afternoon about smoke propagation in buildings, and especially comparing experiments and simulations to each other. Not a complete overview. So if you expected that, sorry about that. It's just some highlights, or highlights some serious problems that we encounter in modeling the experiments and try to fit the simulations to the experiments. Well, maybe first, sorry, I introduced first myself, and then you can introduce yourself.
You're older as me also, so it's okay.
Yeah, I'm older. Yeah. I'm Ruud van Herpen. I'm a fellow fire engineering at Eindhoven University of Technology, and a fellow is kind of, well, let's say a professor from outside to connect the academic world from the university to the engineering world outside the university. I'm doing that only 1 day a week, so that's, but it's very nice to do because I like education, I like research, but I also like project consultancy, fire consultancy and projects. So I think I can make that connection between academic world and the engineering world. So I'm also a fire engineer at Peutz Consultants. Yeah, okay, well, you see my email address and website. If you take a look at the website, you can also see what kind of master projects there are in Eindhoven, what the objectives are, etc., etc. So I think no further introduction for me. Maybe you then, Pim?
Yeah, thank you, Ruud. My name is Pim van Rede. I'm a fire engineer at Accuro. Accuro is an engineering company located here in Holland, doing work on most notably fire engineering projects. Well, while we use the layout of the University of Technology, I am not affiliated with the university, other than that I got my master's in the built environment almost 11 years ago, right now. Currently, I'm finishing the postgraduate program in Ghent with, amongst others, Professor Massi. And Andrea is located somewhere in the back, Andrea Vicerini. You heard him talk yesterday. My thesis is on the numerical simulations of fire-induced smoke propagation, and it uses an experimental data set which was obtained in 2019 by the IFV, now the NIPV, the Fine Institute where we're located right now. My professional interests are the modeling and numerical simulations of fire-related phenomena, and you can contact me here on this address.
Yeah.
So Ruud?
Well, I think your thesis from the postgraduate course is part of this presentation.
Yeah.
And you use the same experiments that a student of mine, a master's student, used. Also modeling experiments in simulation, but you used CFD simulations, FDS, fire dynamic simulator, and my student used CFAST and B-risk simulations, so zone modeling. And well, Pim said to me, well, zone modeling, that is a kind of generation gap. Because I'm much older, I still believe in zone modeling. and according to Pim, well, we have a discussion about that, I think, later on.
Yeah, later on, yeah. We invite all of you to partake in that discussion as well, so please.
To think about that, because I still think that zone modeling makes sense, but depends on boundary conditions. So we divided the presentation and also the discussion in 4 parts. First part, more general about performance-based approach and why internal smoke propagation is important, and especially barriers against internal smoke propagation are important. Then Pim will explain something about the experiments and the CFD simulations, and then, yeah, I think 2 highlights in modeling, 2 difficult problems in modeling fire and smoke source, the fire itself, and modeling of airtightness of separation constructions, shafts, all kind of building elements. So we limit ourselves to those 2 highlights. Of course, there are a lot of more problems or challenges in modeling experiments to simulations, but I think this is enough for this afternoon. Okay, so the first part, performance-based approach and internal smoke propagation. Yeah, I think most of you recognize this picture, 3 assemblies of different boundary conditions, building characteristics, fire characteristics, and human characteristics, and so all boundary conditions with some uncertainty, sometimes a very large uncertainty, sometimes a small uncertainty, but boundary conditions that are significant for modeling natural fires and modeling natural behavior of people in case of fire. So a performance-based approach is always a project-specific approach. So that's why if you do a simulation of an experiment, you can fit it for that experiment, but can you also translate that for other configurations? That's always difficult because you are always project-specific. Human characteristics are changing nowadays, especially in residential buildings. I think that goes for the whole of Western Europe, but especially in Holland, we have an aging population, and that means that it's not always possible that people evacuate by themselves, although we expect that they do that. According to the building code, we have an evacuation concept. But does it then really make sense? So that's also an interesting question when you take into account smoke propagation inside buildings. Main objectives of most building codes has to do with personal safety, safety of the building users, safety of the building assistants, the fire service, and the safety of third-party properties, so the adjacent buildings, adjacent plots. And in all building codes you also find requirements on compartmentation, sometimes on smoke compartmentation, on escape routes, etc., on structural safety. So you can, you could think, okay, there's also something about damage control, because we try to limit the maximum fire spread. We try to limit the smoke propagation. That's true. We try to limit that, but it's not. It has nothing to do with damage control. It's just to gain time for the building occupants to act, and to gain time for the building for the fire service to act, to do something. So they are not absolutely never of them it's absolutely reliable, but those what I call lines of defense are maybe less reliable than let's say the safe escape routes, safe attack routes, and safe environment, who are directly related to the main objectives of the building code. So in all cases, the acceptable risk you can define as the available safe time has to exceed the required safe time. Sometimes we mean clock time. When it comes to evacuation, we mean clock time, real time. And sometimes it's time according to the standard fire curve. So that's not real time, but it's a kind of thermal load, thermal action. The larger the interval is, the larger the safety factor is, the more reliable that risk subsystem is. So I like to think in those risk subsystems. And you see that limiting smoke propagation is also one of the risk subsystems. And I think it's if you evacuate the building, then after some time, smoke propagation is not an issue anymore. If everyone is out, it's not an issue. But evacuation is the concept of the building code. I think in most countries you can say that that's the concept of the building code. But if the left picture, if that are the building residents, and the right picture, that's the escape route, it's a kind of misfit. So you have a safe building on paper, according to the building code, it's safe, according to the requirements, it's safe. But in practice, it's not safe because people can't use the evacuation routes. And so another concept could be, stay in a safe compartment, stay in place concept for non-self-evacuating building occupants. And then smoke propagation becomes even more important, because then, keeping a safe compartment safe during a whole natural fire, that's really a hard job, a tough job. So in the evacuation concept, we try to prevent smoke propagation to the escape route. not for the whole natural fire, but let's say 30 minutes or something like that, when everyone is out of the building, it's not important anymore. And in the stay-in-place concept, then you want to prevent smoke propagation to adjacent compartments, other compartments in the building, but during the whole natural fire. So that might take an hour, might take 90 minutes, something like that. And that's very difficult. And also very difficult to predict, because it depends on air tightness, on internal separation constructions, but it also depends on the overpressure in a fire compartment, or a room in a fire compartment. And it also depends on the air tightness of external separation constructions. And the last one, we have requirements on that because of the energy performance of buildings. We need airtight buildings, because if not, they are not energy sufficient. Okay, yeah, well, this is, I think, also for you not new. Evacuation concept, then we compare the available safe egress time, the E stands for egress then, with the required safe egress time and a safety factor. And in the stay-in-place concept, you do basically the same, the available safe time. You compare with the required safe time, but the required safe time then is the total duration of a natural fire concept. NFC stands for natural fire concept. And because you don't evacuate, people are staying in a compartment that is assumed to be safe. So, yeah, very, very difficult to reach, but I think in theory a nice concept. And yeah, what is safe depends on your assessment criteria, of course. Well, yeah, yeah, you can use several assessment criteria. Here you find the ISO 13571, and FET stands for fractional effective dose. You have also assessment criteria with fractional effective concentration, and a FET value of 1 means that about 50% of the building occupants are not able to move anymore. So if there is no rescue, then they die. So that's never acceptable for an evacuation concept, because people have to move themselves. You have to evacuate yourself. So a FET value of 0.3 with, I don't know exactly the failure probability, but I think then it's about 18%, 0.18. That could be more realistic for the evacuation concept. And yeah, if you have vulnerable building users or vulnerable and non-self-reliant building users, yeah, you could be even more strict in your assessment criteria. In those FET values is toxicity, but also visibility, temperature, everything you want, you think it's important, you can fit in those FET values. And the visibility is especially for the escape route important. And toxicity is especially important when you use a stay-in-place concept and want to know if the conditions in adjacent compartments are still acceptable. Okay, yeah, now, well, here some two pictures, isometric views of a zone model of two different buildings. This is one layer, several rooms attached to a corridor. This is more difficult to say, but this is
3 layers.
Okay, 3 layers and a corridor, and at one side you see also different compartments. So this is how a zone model looks like. You are modeling connections between the zones, some real openings, doors that can be open, or windows in external separation construction that can be open. In both cases here you see, this is where the fire is located. Here you see also fire located. It's a localized fire. So there is no flashover yet. That means that openings in external separation constructions, daylight openings, are assumed to be intact. So there are only a few openings. And then you can calculate or simulate the smoke spread to that building. Characteristic for zone models is that you assume that every zone is uniform, is homogeneous well, a homogeneous mix of temperature and pollution. And so sometimes you can model one room in two zones, a hot zone and a cold zone underneath. Sometimes it's mixed. Then if there are very little temperature difference, then maybe it's better to use a mixed situation. And that's a very simple approach. So because of course it's not homogeneous, but that's an assumption for more or less calculating average conditions. That could be okay if your zone is not too large. So it's computational very fast and cheap, and you can also perform a sensitivity analysis very easy because calculation times are less than a minute, something like that. So you can wait for the answer. So it's from that perspective, it's very efficient, but has a limited field of application. And so then okay, one step more advanced is field modeling, computational fluid dynamics, CFD. Yeah, then okay, here you see a short clip, and you see this is more dynamic. You see also that we can you can predict the conditions in the room at every spot in the room, and as you can also take into account all kinds of turbulences. So it's not homogeneous anymore. So this is more advanced, more accurate, and it has gained popularity due to increasing computational resources. Less efficient, we mean you need more calculation time. And performing a sensitivity analysis with CFD is almost impossible. But a wide field of application. And yeah, then we have two statements that where I started with. It looks like a generation gap, but in my opinion, it's still possible to use zone models instead of CFD models. And you could say, well, it's better to use zone models because you need fewer boundary conditions and therefore fewer uncertainties. So maybe that's more reliable than an advanced model where you need a lot of boundary conditions with a lot of uncertainties. And so results of a simple model are therefore less detailed but more reliable. That's nice. So it's a statement, but I don't know if it's true. It could be true, could be wrong.
On the statement I introduced here, the second one.
Yeah.
So it's not my personal opinion, but to get the discussion going, is that using more complex methods, such as CFD, computational fluid dynamics, should be generally favored over more simple zone models, as the latter simplifies some important aspects of fire-driven flows in a crude and generalizing manner. And what I mean by that is that zone models, well, as Ruud already mentioned, they assume uniformity in the zones, but they also use empiric, semi-empiric plumes, to which Ruud already mentioned, have some limitations when it comes to applicability. Furthermore, CFD allows for local transient phenomena to be predicted, which can be important in an overall fire scenario. So, to get the discussion a little bit going, some reactions, come. Andrea.
Okay.
Thank you for starting the discussion, but I mean, to me, this comes with the level of complexity of the problem you want to solve. Because if you are in a box and you have a fire with a certain heat release rate, you don't even have to use a zone model. You can do some hand calculations and you can understand how much entrainment and how much smoke layer you will get in time. Yep. Then if you have a multi-compartment, that will be important. You can have a zone model, but then it goes into how you have open doors, you have leakages, and all the different models have different assumptions. So to me, it's always important to understand the complexity of your problem, and then based on the complexity of the problem, you can use certain tools.
Yeah. Well, the problem here is smoke propagation inside the building. So we want to know what the smoke pollution is in temperatures, in toxicity, in visibility, in the escape route, and also in adjacent compartments. So that is, therefore, it's not really needed to have detailed information. It's enough to have the information about one room or one part of the escape route to see if it's safe, it's possible for humans to remain there or to use the escape route for some time. I think it's not important to have the exact value at a certain point in the escape route for optical density or toxicity, but that a more average value is good enough for that, for that assessment. So, okay, David.
Yeah. I don't think you need fewer boundary conditions in a zone model. I think that if you are looking for the same reliability, you need in both cases the same boundary conditions. I cannot think of a case that you have a zone model with fewer boundary conditions. I think with CFD models you can do everything you can do with a zone model, but a CFD model a lot of times is overdone, it's a sort of overshoot.
Overkill, yeah.
Another thing is that CFD models, if you are talking about only transient smoke propagation, we assume, I think we know that that can be predicted quite reliable. But in CFD packages, there's a lot more like paralysis models, yeah. That kind of stuff. Yeah. And that's really beyond a reasonable form of validation. So the CFD models also hold a risk that you do things that you that are not validated in that kind of models.
Yeah, we come to that. I agree in modeling the source is very important because there starts the temperature production and the smoke production. And modeling the source in zone modeling is very simple. So that has its limitations. Well, we come to that because in CFD you cannot do it in a more advanced way, but very often we don't do that. Also in CFD we do it very simple. Yes.
Yeah, from my perspective, comparing CFD to zone model in like case-by-case basis is a little unfair because of the amount of resources necessary for both simulations. So if you could imagine a situation where you would devote the same amount of resources you'd use for CFD, for zone models, you can run 100 or 1,000 simulations in place of one. And now the question is not really whether a simple answer to one question is better than a detailed answer to one question. It's whether a simple answer to 1,000 questions is better than one answer to one question. And that opens a whole new world of possibilities where zone modeling absolutely shines. And I don't think CFD will reach any of that because we seem to complicate our models quicker than computers develop their power. Yeah. So this is a very bright advantage of zone modeling. And when it comes to like case-by-case comparison, the thing that you cannot see with zone models is really mixing at the boundary of layers. And in some cases, like the car parks that I presented yesterday, this mixing can be absolutely critical for how car park fills with smoke. Because you may still remove a lot of smoke from the car park, but one little vortex that spins destroys everything, and you will not see that in zone model because you are not solving for that interface. You're just solving mass transfer between one zone and another. And the same would go if you have very complex geometry of, for example, roof or ceiling with a lot of, or staircases, with a lot of tiny details that influence the flow. Then you definitely need CFD, but for other cases, well, you're probably better with zone models. Unless you want to charge a lot of money, then you need CFD.
Yeah. So for complex geometries, you should always use CFD calculations. I like your argument of
even if a very simple case. If you have the most simple case, a fire in a room, you will see in CFD, for example, smoke flowing on the roof and then bouncing at the wall and coming down. Something you never see in a zone.
You get
that's the simplest case we can imagine.
You can get some very local effects, which you see which you can actually simulate and predict with CFD, and you cannot possibly do that with zone model. Patrick.
Yeah, I just want to jump on this because I think that's an important thing where if it's necessary, you can see that difference. Because if I have an extremely old report of the looking to both zone model and CFD model to simulate the Sweetel fire in Antwerp. Some of you maybe were almost born then, but anyhow. So and there we could see that there were problems in the evacuation because the smoke layer of this two Christmas tree went down on the wall and made problems to find where the access. So you really have to evaluate your result. In other cases, this old model maybe would have worked well, also, because I'm also agreeing with Andrea is that we can even in certain cases use simple engineering models, and sometimes maybe we reach a little bit too high level, but if it's getting more complex, then of course you have to use CFD. So I think it's somehow a step approach that you can, if you want, you can try first with the simple engineering model and zone, but if you see that the results are maybe critical or uncertain, then maybe you have to go for a CFD model. It's a bit maybe a step-by-step approach.
So sometimes localized effects have large consequences for the global conclusion. Yeah, Peter.
I think it's clear that when the problem gets more complicated, zone models lose their abilities. If you apply a zone model to a 5,000 square meter car park that is 2.5 meters high, forget it. It cannot give a correct answer whatsoever.
Yeah, because
and the CFD model is capable of providing answers for much more complex situations. But as soon as the problem gets somewhat complicated, the CFD model is beyond its zone of validated application. So it provides answers, but they are not validated.
No. So there are certain dimensions you have to take into account, especially the height and the width and the depth of a zone, of a compartment. Because if you exceed those dimensions, then it's the loss. Then then there is no. Well, there is never a guarantee of a homogeneous zone.
I believe that Peter was talking about the validation of CFD, not per se.
That's one of the problems. That's what I wanted to ask. We, as managing director in type IA accreditation service, are often asked to certify, to do an inspection on the systems, but we can't certify because we don't know which system is used. And if they have the same value, and if they are validated, or because they has to be certified. By what?
And what do you mean with systems then? A smoke extraction ventilation system, or
If the smoke extraction system has been calculated using CFD, for instance.
Yeah, that's the problem.
No way to certify it. There's
no way to certify.
No, there's no standard for that, so that's the problem.
But that's still a problem. Because
and
they often ask us for the...
Well, you should say, sorry, can't do it.
Okay, well, one last, because then we have to go further. Andrea.
There's the last point. No, it's important to remember that we are like fire safety engineers, firefighters and professionals that have been studying to get into these positions. And we shouldn't forget that we have a brain and not just get immediately and go into CFD by definitions, because we will get results that can be easily accepted just because they have a fancy interface. Sometimes it's hard to say that I made a hand calculation. You have an atrium, for example. An atrium is a big box, and you want to see how the smoke layer, for example, comes down. Yes, you can look at the corners, but then if you have a layer at 5 meters below the ceiling, you want to see how long it's going to take to reach that point. You just need a simple increment model, then you can understand that.
Yeah.
And you shouldn't go always to the difficult because it's easier to sell, but you have to think that you have tools and you, in your brain, you can understand which is the best tool, but also, as I tried to present yesterday, you, as a smart person, you should already predict more or less if your result makes sense or not. If you're not able to understand if your result is correct, if your result is correct or not, you shouldn't use that tool.
Yeah.
Because
Well,
Yeah.
so you say that, but if you use a CFD model to calculate a large car park, multi-story, filled with cars, with a mechanical extraction system, jet fans all around, you get a result, but you can never say with any degree of certainty that your result is correct, to within 10, 20, 50 or 200%. You agree?
Yeah, but you use the tool as a qualitative understanding of how your system will behave.
As you showed,
Yeah.
that you can use, I think that was a very valid way of dealing with this. You use the tool, the CFD tool, to calculate differences between relatively small differences between validated situations,
Yeah.
but not beyond. And what we are doing on a daily basis for design purposes is using the tool for a situation for which we do not have any validation at all.
Oh, and worse is that we don't even do a sensitivity analysis, because that could help if you don't have
It could help a
But
little.
you could say the same thing for zone modeling to some extent, right?
Yeah, of course.
It's not validated. You know, you use the Thomas plume or you use the McAfee plume. You know,
Yeah.
that's also under very specific circumstances that a training grade.
But those circumstances are known.
Yeah, absolutely. Yeah.
So you can say within definable bounds.
Yeah.
To what degree you are.
For this crude number, you can use that and that.
So you know that you are 20, 30 or 30%.
Yeah.
You may be 20 or 30% wrong. I never hear
some values for.
I never see that for a much more complicated calculation using CFD.
That's true.
Oh, but I've also seen studies. I believe Wojciech was involved in one of those. An atrium study, which, for example, the Thomas plume showed an error of 150% or something.
Yeah.
And that was also an axisymmetric and normal plume.
Yeah.
That's 150% is a lot. You can't engineer with that. No, absolutely not. And that's where CFD shines, in my opinion.
Yes.
Yeah.
Last comment. Since we don't have these results validated, means that we cannot build complicated buildings. Because we have architects that send us projects and you don't have models, validated models to verify if your smoke would propagate. So this means we cannot build that buildings, right?
You can build them, but you should warn your architect that you may be 100% wrong in your calculated results.
So
you should take a safety factor to compensate for that.
in terms of the AST/RST analysis, you should use a large safety factor, because of the uncertainty in the results.
Even if you use CFD.
Even if you use CFD.
Yeah, but Patrick, Peter, but for tunnels, we routinely, I would say tunnels would be more complicated than car park.
It's a one dimension less.
Yes.
It's not one dimension less.
Yeah.
If you have 20-meter wide tunnel, it's not one dimension less. It's extremely complicated. And we routinely achieve the same results as in CFD. In Brussels Schumann projects, we were terrorized by matching the CFD results with the calculation on the side, and it was like 3 kilometers of the tunnel with a complex intersection. So we matched it. On airports, like there were studies on airports. We've done hot smoke tests on an airport in Warsaw, which we simulated. We match. I cannot tell you that we get 17% error or 16% error, but it was not 200% error. And I think flow is a flow. If CFD doesn't work, then the all airplanes from the sky should fall down and we should kick back.
Actually, they do that. You know?
So
simple airport.
CFD works, and cold flow validation is still a good technique because it's very difficult to expect that we will show proofs of hot smoke validation for 5,000 square meter.
Shall we just skip the discussion questions in the sheets anymore? Sorry.
At least there's some nice interaction, right?
Yeah.
Okay. Well, to explain a bit about experimental
I'll take it over
simulation.
from now, for this part. So for my thesis project, which I've already explained, I've done some CFD simulations and I compared them with the experimental results from the outer water experiments. Oh, why on you? That's not Spatie. Spatie? Oh. Thank you. So first of all, to go into the smoke propagation experiments which were carried out in 2019 by the Institute of Physical Safety, the NIPV, here in Holland. That experimental campaign consisted of 18 full-scale fire experiments, and during those experiments they've they made some variations in the boundary conditions, and one of the main variations that they've done is change the level of available ventilation. Well, all but two experiments, the fire source was composed of a polyurethane filled two-seater, which is shown here at the bottom right. It's a shame we don't have a laser pointer here. Yeah. You can see that it's elevated a little bit. It's standing on a weighing scale. So during the experiments, the mass loss rate of the sofa was measured. So we have an indication of how much mass actually pyrolyzed during the experiment. Also, in both the apartment and the adjacent corridor, and also in other apartments, but I'm not going into the other apartments. I'm limiting myself to the apartment with the sofa and the corridor. Gas concentrations were measured, so oxygen, carbon monoxide, and carbon dioxide, for example. Also, temperatures were measured using thermocouples. Pressures were measured, and visibility was measured. Now, just a statement. As far as I know, you were not involved in the experiment. So, if you have any in-depth questions relating to these experiments, please ask Liebe. So, for the CFD study, to go into the setup, what you see here is actually the floor plan of the floor with the fire seat. You can see the two red blocks there. That was the location of the sofa. In either one of the apartments, the sofa was placed and ignited. It was located in a corner. There were reasons to do that, but I'm not going to going into too much detail there. During my simulations, I've modeled 3 measurement trees, and then in those measurement trees, which you can see here, is number B1, B6, and B5. So 1 in the apartment and 2 in the corridor. There were thermocouples, pressure gauges. There were also radiative heat flux gauges, but I didn't use them in my CFD study. And visibility meters, so light intensity meters. I set up 3 cases. I studied 3 cases, all with a varying level of ventilation. The first one had the balcony door open, so the top there you can see this window frame which had a door in it, which was open during the experiment. And in the other 2, so 2 and 3, that door was closed. In all the experiments, the door between the apartment and corridor was opened 300 seconds into, so 5 minutes into the experiment. In 2, it was kept open in case study 2, and in case study 3, it was closed later on. So, if you have any questions, please do not do ask them. Yeah, Peter.
Other openings, ventilation.
No, what they actually did is they measured the tightness of the apartment prior to the experiment. So they did a blower door test. So we have an indication. It's an indication of the airtightness of the enclosure. It was in the order of magnitude of 200 centimeters square.
To the outside?
No.
No,
overall. Yeah. I believe you had a...
That means interior and exterior construction together.
Ventilation shafts or systems?
They're open during, they opened them during the experiments, so they're included in that leakage area. Okay. Yeah?
So there were no firewalls in the ventilation system?
No, it's an old apartment building. Okay. No firewalls. It was just a shaft, natural ventilation. So for my simulations, Ruud already mentioned it. I used a fire dynamics simulator. It's a CFD tool by NIST. Andrea used the same software, so I'm not going into too much detail there. the heat release rate of the sofa, I actually derived that from the Maslow's rates, which were measured during the experiment, and I multiplied that with the effective heat of combustion. Now, one important thing is that they did not carry out calorimetry. So we do not have, so that's a tongue breaker there. But so we do not have a real good value for that effective heat of combustion. Yeah, typically for polyurethane foam, we can expect somewhere between 16 and 25 megajoules per kilogram, depending on the combustion efficiency and the chemical composition of that fuel. So what I did, I actually took the thermocouple data from the experiments, and from that data I derived what effective heat of combustion I would expect under those circumstances. That's by means of an energy balance. Using the oxygen measurements in the apartment, I was actually able to calculate or approximate some form of a equivalence ratio, which says something about the level of underventilation. It's the ratio between how much air you need for combustion and how much air there is. And I calculated some yields which are imposed in a static manner in FDS. And my question to you is, when we're dealing with underventilated fires, what is the main issue with using static yields? Static species yields for CO, for soot, anyone?
They're not static.
Yeah, absolutely.
Yeah.
Oh, they're transient, you know. At the moment a fire becomes underventilated, we start to see a very exponential increase in both soot and CO generation. Also HCN, so
yeah, I think all pollution.
All products of incomplete combustion, they showcase a very exponential increase. So this is one of the main, how do you call it? Beperkingen?
Challenges in
challenges in FDS.
But not only in CFD, it's the same issue, the same problem in zone simulations. Also
in CFAS you can prescribe a soot yield and a CO yield per time step or something. Yeah, that's possible, but that's also very rudimentary and very tricky. So this is one of the main drawbacks of using FDS or any CFD package, as far as I know, in the simulation of underventilated fire conditions. Now, as you can see here, we expect a heat release rate ranging from 700 kilowatts, 750, up to 2 megawatts, depending on the level of available ventilation. Now, before I go into the results, I have prepared a short movie for you guys. Before I press play, I'd like to go over the things that you're going to see. So you're going to see a fire plume originating above the fire seat, a smoke layer that's descending over time, and at some point the fire plume is going to entrain, because that's typically what they do as a result of turbulent mixing. They're going to entrain. It's going to entrain its own combustion products. The smoke layer drops below the fire plume, and it's going to entrain its own combustion products. It's going to entrain the smoke layer. That's what we call vitiated combustion in fancy words. After that, the video is going to move to the corridor, and then you can see the smoke leaking through the apartment door as a result of the overpressure in the compartment. And afterwards, when the door opens, the corridor is almost instantaneously flooded with smoke. So you can see the smoke plume, the fire plume. You can see already there it is. It's 16 times real time. So it's entraining its own combustion products. There you have smoke leaking, and after a while, the entire corridor is flooded with smoke. Now that looks cool and all, but how realistic is it? That's one of the main things Peter was talking about. Is it fit for purpose?
If you compare them with existing film materials from tests.
Well, I'll later on. What you can see here is results for O2, for oxygen, and for carbon monoxide in the apartment, using static yields. So take that, keep that in mind. What we see for O2 is that, well, there are some initial differences between O2 levels in the apartment. I'm not going into that any further, but that's relevant. You can see that the trends are captured accurately by FDS. You know, at some point, that fire, well, anywhere, I believe, between at around 30%, you can expect that fire to become underventilated, and we can expect some what we call flame extinction. So the flame is the fire is quenched as a result of, well, there isn't enough oxygen for the combustion to continue. So that extinction phenomena is predicted quite well by FDS in this situation. So it's case study 1 with the balcony door open, quite well ventilated. And for CO, we can see that while the differences are quite pronounced, it's in the order of magnitude of at least in the initial stages of 1000 ppm. But taking into account the fact that I had to impose a static yield in FDS, this is, well, a quite nice fit, right? Now, when we move into, yeah?
The sheet before, the blue line,
yeah.
And the red is
the blue line is the experimental results?
Yeah, it's then the wrong description.
Yes. You know what it means.
Yes. Yeah, okay. But
oh yeah.
FDS.
Yeah. Yeah.
Oh yeah. Oh, there you have.
Yeah, you mean experiment.
I took I copied this out of my thesis, so there you have the first. Now, when we move into a fire that's even further diluted of oxygen, we can see that FDS really starts to have trouble. That the FDS really starts to have trouble. FDS only reaches 10% volume percent in oxygen in its simulations, while in reality, during the experiments, values up to 2 to 3% were measured. So that's a very hypoxic environment, very, very hypoxic. You're not going to have a nice time when you're walking there. So for CO, well, once more, static values, static yields. So what we see is that FDS initially severely overestimates CO yields. So when we were going to do, for example, a tenability study using those static yields, we're going to be very conservative, maybe over conservative, and make over investments. But that's a discussion for another time. And afterwards, we can see that as the yields tend to increase exponentially in reality, FDS underpredicts everything. In this case, the culprits in this scheme are the static chemistry, which I talked about earlier, but also the extinction model.
The two graphs are more or less related to each other. So
yeah, absolutely.
The underestimation there is corresponds to the overestimation in the other
but
diagram.
what would happen if, for example, we would force FDS to go lower here? What would happen with the CO level then? Yeah. It would exponentially, or it would very, very highly overshine the experimental data. A little bit theory about flame extinction. It's an active field of research of flame extinction as a result of, for example, introduction of a suppression agent like CO2 or water vapor, but also as a result of oxygen dilution. It's an active field of research, and as far as I'm aware, and I'm not an academic, but not one perfect model exists currently. So there's all it's all empiric. In FDS, we use the critical flame temperature concept. It uses 2 parameters: the lower oxygen limit and the critical flame temperature, or adiabatic flame temperature. Depends on what name you prefer. That concept relies heavily on the cell temperature. Now, not to be too technical, but in LES, which is a method for using CFD, which also is used by FDS, the cell temperature depends very highly on the used mesh resolution. So to get my bearings, so to effectively use this model, the critical flame temperature, we need to use quite a highly resolved mesh, a very dense mesh. You can see here that, for example, on the left side, I've used a mesh by 2.5 centimeters, which is already very, very low when we're talking engineering studies. It is composed of a total 9 million cells. It took more than a week to run 400 seconds on 100 cores, so that's not practical. And the right-hand side, you can see 5 by 5 by 5, 2.7 million cells. But you can see the difference in the flame. It's not only like you called it more beautiful over when we talked on Teams. You know, it's more resolved. It looks better, but the heat release rate that's predicted is also quite a bit higher with the model used here.
Yeah, but it's also a large error simulation, so that means that every moment you have a different flame.
Absolutely, yeah. So you need to time every.
So I don't know if it's really comparable, because.
Oh, but actually, if you plot the heat release rate, you can see that there's a difference.
You can see that,
100 to 200 kilowatts. So that's quite a big difference. Yeah. Now, what I mentioned earlier, when I'm running my simulations, and I run a lot for my thesis, running them for 1 week on 100 cores, that's just not practical. That's hell. So what I did, and that's more of an engineering solution, I forced FDS to give me the right results by lowering the lower oxygen limit and the critical flame temperature. This is crude, very crude, and not justified. Yeah, so keep that in mind. So. As I mentioned earlier, I lowered the critical flame temperature and the lower oxygen limit. And you can see here in the parametric study what that does with the O2 and also with the CO. Note that I changed from a static chemistry model to a two-step model in which first all the fuel is reacting with O2 to CO and soot. And afterwards, the second step of the reaction, it once more reacts with oxygen to form CO2, should there be enough oxygen available. Now, the only variable in this is the oxygen available, and that's very, very rudimentary and also not very justifiable because chemical kinetics are much, much more complex than what we than just imposing a variable of oxygen. But you can see here that the O2 or the CO, so the carbon monoxide, actually quite nicely follows the green line, which is a value of lower oxygen limit of 0.08 and a critical flame temperature of 654 degrees centigrade. So I used this data or this settings for the other case study 3, and guess what? No way.
Yeah.
So don't hold your breath. It says it there. The same settings did not yield good results in case study 3. This is an indication that you should be very, very careful when you're going to use FDS to model and simulate underventilated fires. Be very careful. CO formation is highly complex, and the chemistry more or less dictates the entire simulation. That's the way FDS works. And we can currently not predict that at a good enough extent. Be very careful.
How does this work with more complex combustibles?
It becomes more complex. No, yeah, it doesn't. This is just a simple polyurethane foam. Well, simple. There's nothing simple about polyurethane, but the reaction scheme, one-step reaction scheme, is quite well.
Yeah. It's quite clear.
Yeah. Now going into pressure buildup in the apartment. So what I mentioned earlier, they also measured pressures in the apartment and the corridor. The corridor I'm not going to talk to that much about. Ruud's also going to go into leakage modeling, so I'm going to go over it a bit faster. I've put 3 correlations on the screen here. Once more, not going in them into too much detail, but be aware, or you should note, that pressure buildup depends more or less on 3 variables. That's the heat release rate. The heat release rate is predicting. It's dictating the temperature in the apartment, and also by that way, it's also dictating the pressure buildup, because hot air wants to expand, and if it cannot vent away to the outside, it will increase pressure in the apartment. Also, the leakage area, what we talked about earlier with Peter, and the leak pressure exponent, the N, which you can see here, which is typically used to take into account that leakage area, which I've mentioned earlier, starts to increase at higher pressures, because seams and joints tend to open up under higher pressures. So we take that into account by introducing that exponent N there.
Sorry, can I ask a question?
Sure.
That relationship must be valid for one specific type of leakage.
Yeah.
Yeah, or if you measure an overall
Yeah.
leakage of a total separation construction, you can use that.
It
That
was
is not a
measured,
specific type,
for
but
that room, right? So it's the air tightness of that room that was measured.
Yeah.
And we have, well, actually, I believe Niemann, when you were at Niemann, you carried out this experiment, right?
Yeah.
Or one of your colleagues.
One of our colleagues.
Yeah.
Yeah.
So what they did is they pressurized it. Yeah, I don't have to explain why, how to you how it works, but they overpressure, they overpressure the room, and they measure the.
What I mean to say, if you have a door opening outward,
And that's not an issue.
Different relationship
Absolutely.
from the same door opening inward.
Yeah, you'd have a different
So
leakage.
This is not a universal
No.
leakage area.
But we tend to treat it like that as it is. That's universal.
Aha.
Yeah. And it's especially for small air leakages. If you have an open door, an open window, the leakage exponent, the pressure exponent,
that's 1.5.
it's almost 1.5 in all cases. Yeah.
Then you're also going to introduce the Bernoulli coefficient for turbulent flows and all that, but that's not that's a little bit too complicated now. What you can see here is what altering these parameters does in your simulation. So introducing a higher leakage area will result in a linear decrease in pressure. For the exponent, as it's exponential, it will result in a higher exponent will result in a exponential decrease in pressure, which you can also see here. So we have this is the 0.6 leakage exponent, and this is the 0.48 exponent. And you can see that it's well, as you go lower, the difference between the lines becomes bigger. For the heat release rate, that's more or less linear, and you would also expect that when you look at this correlation here. Oh no, it's quadratic itself. It's quadratic. There you have it, but it's more complex because that correlation which I've shown earlier is a very high simplification of reality. Now we have this is the overall results of pressure, which I find in the apartment. You can see that the trends initially are, well, they're predicted to a well enough extent. Note that the mass loss rates I've used were time average, so I averaged away the ups and downs in the measurements. The pressures are predicted quite nicely in the initial time frame. At some point, the door towards the corridor is opened and it's closed again. And afterwards, we can see this enormous peak, both experimentally. You can see this. I'm not sure if you can see this here, but the dotted line, that's the experimental value. This is also experimental, but using a different measuring equipment. And the orange line is the FDS results. Can anyone explain why that? What happens there after that door is closed? Why we see an instantaneous peak, but also an instantaneous decrease in pressure?
So small explosion of the gases when you let oxygen.
I'm sorry?
You let oxygen in, so the gas is ignited immediately.
Yeah, you have this. Indeed, you have your heat release rate. Your history just skyrockets at that moment. But why does that? Why do we see that sharp decrease afterwards?
The lack of oxygen, actually.
Yeah.
Yeah.
So it's underventilated. It's become underventilated. Absolutely. This what we typically see when a fire becomes underventilated, a sharp decrease in pressure, instantaneous. Now I'm going to skip the other two. They're a little bit more complicated. A little bit more on soot and visibility. They've also carried out light attenuation measurements. So they have something, they've derived the visibility in the corridor for the during the experiments. And that visibility is depending on more the soot concentration in the corridor. Soot formation in fire is also an active field of academic research. It's also very complex. You can see here the soot conglomerates, which I've copied from the SFP handbook. And note that the scale is in micrometers, so it's very, very small. The soot generation of a fuel is highly dependent on the chemical composition of the fuel. So a methane fire will result in a significantly lower soot generation than, for example, a polyurethane sofa, which burns very filthy. It's also heavily dependent on the level of available oxygen. And what we typically tend to do in engineering applications is that we introduce a soot yield, which we also do for CO, but for soot it's also the case. And that yield is a unit which says something about how much soot is generated per mass, unit mass of fuel.
Yeah.
You have actually something more about that, right?
Yeah, but I think we skipped that because when you finish, I think I'll show something about air permeability but
how's the time?
I think we have to end at 3
let me
o'clock.
skip this. I'll let you do this. The next part. This is not very interesting anyway. Okay. Again, I have I can show you this picture, which shows the soot the propagation in the corridor, side by side for left the experimental value and right the FDS simulation. You can see that it's more or less a nice fit. So, Ruud.
Yeah.
Sorry, I took so long.
Well, yeah. I think there is some repetition in my part and your part, but more specific for zone modeling, source modeling of important for internal smoke propagation. Yeah, I think. Well, maybe a few highlights, and then I want to end with air permeability, because then we can stop in the right time. But this is what you meant with yield. It's kind of a scalar multiplication factor we put on the rate of heat release, and that's only more or less valid if you have a fuel controlled fire. But if it's ventilation controlled or oxygen controlled, however you want to call it, then that's what you see in this graph. It is fuel controlled means that it's stoichiometric combustion. So that is equivalent ratio less than 1. If the ratio is increasing, then it becomes an increasingly more oxygen controlled fire, and then you see that the yields are also becoming worse. So you see soot production, CO production, depending on the fuel. And that's very hard to predict because you don't know exactly in what kind of range you are. So it's always very difficult. That's what you already stressed too, Pim. That this is in case of source modeling very difficult when you have an underventilated or an oxygen-controlled fire. You don't know exactly in what ratio you are.
But also when we're dealing with sprinklered fires.
Yeah, the sprinklered fire is the same. It's the same issue. Yeah, it's the same issue.
That's also problematic.
Yeah. Yeah. Okay, so that is a kind of explanation. More explanation on that. Yeah. Okay. Maybe I mentioned some results of my master student, Mark Scholman. He used the same experimental research as Pim used, but he modeled that in B-risk and CFast, and so the same fire scenario, in a 2-seat sofa. This was his model. So two levels, corridor with adjacent compartments. No internal separation construction in the compartment. So one compartment, one room is total free open area. So that's maybe not quite realistic, but his way of modeling. And yeah, this is for you difficult to read, I think, but here you see experimental data on temperatures in time compared to the CFAST simulation and the B-risk simulation. Yeah, I can't see colors, so I can't explain the lines to you.
So how did you grade this then?
This comes from Mark's report, so I didn't produce this. But this line, blue, I guess.
Yeah.
The blue line is B-risk, and the other two are the experimental data and CFAST. And you see here that in temperatures in the fire room, and the same goes for the temperatures in the corridor, that there is a better fit with CFAST to the experimental data than with B-risk. And that's typical, that's a bit strange, because in fact, it's the same, more or less the same model. There is one large difference, I think, between B-risk and CFAST, and that's CFAST uses a fixed lower oxygen limit, so you can give that as a 10% value or a 15% value, whatever you think is realistic. And in B-risk, it's like in FDS, it's temperature dependent, and so it's generating its own lower oxygen limit depending on the temperature. And I'm not sure if that's really correct. Well, maybe I can't say that because I don't have enough insight in B-risk, so I can't say that. But
wouldn't you expect, if that's the case, right?
Yeah.
If it's temperature dependent, wouldn't you expect B-risk to yield an ultimately higher heat release rate than CFAST?
Yeah, I don't know, because that depends on is the lower oxygen limit related to the upper zone temperature or the lower zone temperature? I don't know. Or is it another temperature specifically close to the fire source?
At some point, you don't have any zones left.
No,
just,
no, it's because it's in the fire and the plume.
I'm sorry?
CFAST has a corridor submodel.
Yeah, absolutely.
That's developed from FDS simulation. So, and I don't think B-risk has the exact same corridor model. So B-risk may treat corridor as one uniform zone, whereas CFAST could do some.
That's a revised ceiling jet, right? That they use.
No, even further, because it's based on CFD simulations. It's kind of a weird model, actually.
Yeah. Okay. So yeah, you see also oxygen concentration in this case in the corridor. So I didn't use all his, but some graphs from the report from Mark. Also, well, yeah, it's a bit. I think this is the black line, experimental data. This is CFAST and this is B-risk. Yeah, in both cases you see. Okay, the lowest concentration, the dip in the oxygen concentration, corresponds very well. But then you see after that there is a difference between the data and the simulation in both B-risk and CFAST. So it's you can try to fit it. Sometimes it fits on temperatures, but then it doesn't fit anymore on concentrations. And so it's very hard to have to fit in all aspects. That's almost impossible. Okay, so yeah, well, this was my question. B-risk is lower oxygen limit depending on temperature, but that looks more advanced, and I think in FDS that's the right way to do it. But how do you do that in a zone model? For me that's not clear, and then I didn't go very deep into this question, but I'm very curious about how that is done in B-risk. I'm not sure. Not many of you experienced in B-risk, I think, more in CFAST.
Yeah, because it runs on my computer, CFAST doesn't.
You need to change the settings to United States.
Yeah, okay. Yeah, I think that flame, you already talked about the flame extinction model, and this is basically the model in FDS, Fire Dynamic Simulator. So that's a time-dependent model, sorry, a temperature-dependent model for burn and no burn situation, depending on temperature and the mass fraction oxygen. And so that, well, would be nice if you could cooperate that into a zone model, but I'm not. For me, it's curious how you could do that. We have 5 minutes, I think. So okay, okay. Well, no. Just well, I skipped some. The problem of I think both zone modeling and FDS modeling is let's say that you have different rooms that you are connecting to each other. Sometimes with real openings, because if door opens or if a window is open, then you know the opening. If you have a ventilation opening, you know the opening area. That's not a problem. The problem is, well, let's see the air leakage in joints, connections, seams, etc. So the very small openings where you also have a different pressure exponent. The volume flow, that's the upper equation, the Q or the V with a point. The volume flow depends on the pressure difference, and the pressure exponent is between 0.5 and 1.0. And for large openings, it's 0.5. So it's the square root of the pressure difference. So then you calculate the volume flow. If you have very small openings, then it becomes more or less laminar flow. So that means that it's in between 0.5 and 1.0 as a pressure exponent. What we do is that we translate that into an equivalent opening area. That's what we do, I think, both in FDS and in zone modeling. So for okay, so this is, for instance, a very small opening. That if you want to model that right in FDS, you need a very fine mesh. So that's almost impossible, I think. And also, yeah, you have a flow exponent that's in between 0.5 and 1. And the problem with zone models is that you can only calculate large openings. So that means, per definition, a flow exponent of 0.5. So a translation in equivalent opening area for large openings. Okay, it's clear, with a fixed flow exponent of 0.5 because it's a large opening. Yeah, the difficulty that we have in modeling in FDS means that you have, if you do that in the right way, you need a very fine mesh, and here you have a larger mesh width. So yeah, that is difficult to model. I think it's almost impossible to model that.
That's
right
millimeter size mesh is what
yeah.
you need. That's no way.
Yeah, no, but that's what you need for those openings. So what we do in practice is what we also did in the experiment in Oudewater is that we measure the total leakage of the external separation construction, so the leakage of the building in total. That's what we need to do for energy efficiency of the building. We need to know what the air leakage of the external separation construction is. So we have measurements methods to do that. We can do that. But then still we don't know what the internal leakage is. But what we also can do is just measure a whole compartment, an apartment inside the building. And so then we know the air leakage of the external separation construction. We know the air leakage of the apartment as a whole. That's partly external, partly internal. So if you have those two measurements, yeah, this is an this is a graph of a picture of the Dutch standard. I think it's NAN 2686 for measurements of external separation construction. You see, measurement device, a door with a ventilator, and we can regulate the ventilator, so we can create a pressure volume flow with different pressure, with several pressure differences. Well, if you do that for a building as a whole, you have the external separation construction, the leakage. Well, I only have one project where we did that in a proper way. That's all about building in Hilversum already several years ago. And you do that for one apartment. And you can also have an idea about the air permeability or air leakage of the internal separation constructions. But that's the total internal separation construction. So floors, walls, walls to adjacent compartments, walls to the escape route, all together. But you see that here we define that as a volume flow at 10 Pascal. That's the QV10. And then you see that the exponent here is not 0.5, but it's, in this case, 0.645. And for external separation construction here is 0.8. So it's different. And that means that if you translate that in an equivalent air equivalent leakage area, that it depends on what your reference level is for pressure difference. Do you, is it acceptable to do that with 10 pascals, or maybe we need to do that at 20 or at 1 or at 50 pascals? But you get always a difference, and that's because if you have, for instance, this is the pressure difference. This is your volume flow with a linear. So this is, let's say, with an exponent of 0.5 for a large area, and if you have a higher exponent, yeah, you get something like this. So, and then, yeah, it makes it different if you define your air leakage opening at 1 Pascal or at 10 or at 20 or at 50. That means that you have an underestimation of your air leakage at higher pressure differences and an overestimation at lower pressure differences. So, yeah, how can we fix that? Or should we, yes, maybe create stepwise a kind of an input file with an air leakage area depending on the pressure difference on the separation construction. Maybe that will be the nice thing. So
I believe we need to.
Yeah, I think we have to. Yeah. We have to end. But here you see that it really makes a large difference if you do that at 1 Pascal, 5 Pascals, 10, 50, or 100 Pascals. So you see that the equivalent leakage area really depends on the pressure difference. Yeah. I'll stop right now then. Okay. Okay, so if you have suggestions how we can solve this in zone models, in FDS models, well, I showed you my email address. Maybe it's also on the last slide. So that would be an. We skipped this all. Oh, that's too fast. Yeah, here you have the email addresses from Pim and from me. So suggestions are always welcome. So. Because these are the problems that we're facing now in modeling smoke propagation inside building. Yeah, if you can do that in a more accurate or more realistic way, you will be very welcome.
Any questions before we
go to the drinks?
Peter.
You say CFAS doesn't have the possibility to define small openings?
Yeah.
Small linear openings? I think it does.
Yeah, you can.
Yeah.
I believe with one of the latest releases, you can actually include pre-specify a leakage area.
Yeah, but
an exponent, including an exponent.
No, that's not including an exponent. I think it's still the same issue. It's correct. You can give in a leakage area depending on a separation construction, or maybe it's for a separation as a total.
For an apartment, for an apartment.
Yeah, for an apartment that's total. But
content, but that's a different package.
Yeah,
that certainly has it.
That's a flow package.
Yeah, and transit flow certainly has it, but that are building physics packages, not specific use for fire conditions. So, yeah. No, you're right, Peter. I think in the newest versions that's possible, but still you can't give in the pressure exposure.
If so, I haven't found it. Any more questions? If not, then I assume we grab a cup of coffee and move to the next.